whole world view that we want students to begin to develop and embrace, starting, actually, my daughter teaches pre-kindergarten, starting in pre-kindergarten, or she teaches preschool. Starting as early as you like, building across the years a deeper understanding that allows people to begin to face these kinds of issues. Furthermore, research on learning says that's what works. Right? If you want knowledge that transfers, knowledge that is not just good for answering questions on a test, but is good for solving a problem that you meet in your life, then you have to practice that. You have to use your knowledge to do something with it, and it becomes more part of the way you approach problems than if you just learn it as something you need to remember. So the research on learning has told us what works better, and we should be doing that in order for our students to learn better. And so all of that is built into the thinking that went into the framework. There was a two-step process. This was the wisdom of the Carnegie Corporation of New York, who actually funded both pieces of the progress. The first asked the National Academy of Sciences. And at the time I was the chair of something called the Board on Science Education, so I was one of the people that was asked, could you do this? And I said, I would love to. And we made a committee that had 9 scientists, all of them members of the National Academy of Science, 2 of them Nobel Prize winners, and 9 people of equal status and equal importance who were educators, who were people who did research on learning, or had been a state science supervisor, or had been a kindergarten teacher, and now I was a teacher in a school of education, training teachers. People who really knew what it was like to work in the real classroom and knew the research on learning. And that combination was asked to decide what is most important for students to learn. And that's what the framework is about, trying to figure out the important messages and how they build across the years of school. And then the second step was to take that document and turn it into a set of standards. That step was led by a chief, and 26 states signed up to be part of the process, California included. And that meant there was a team from each of those states reviewing and iterating the process as it worked along, so that when the standards came out, they had gone through many iterations before they went through public reviews, and then they went through another iteration on public reviews and came out as the next generation science standards. So I call this talk Science for the Next Generation. This is not a one-day change. This is a change which will probably take us 10 years to get there really all the way. That doesn't mean don't start tomorrow, but it means don't expect to have it all in place as you start. Be willing to step by step change practice and get to where you need to be, because anything worth doing is worth investing some effort in. And we, the committee and the standards developers, probably didn't get it all right. So it's going to have to take some work to get it to the place where it really, really works in the classroom. So the framework leads to the standards. That's not enough. To have everything work, you need everything over on this side. You need assessments that are aligned to the standards. You need curriculum resources and materials that are aligned to the standards. You need teacher professional development and teacher pre-service training that is aligned to the standards. And you need instruction in the classroom that is aligned to the standards. So the standards are just guidelines. They are, of course, what will eventually be assessed. Nobody's quite figured out how to do that yet for the next generation science standards, so we still don't know what those assessments will look like. But I hope they look quite different from what you've seen before in terms of state science assessments. And I'm working on that front too. Okay, so what are the goals of the framework? First of all, science has all too often been a set of disconnected lessons. At elementary school, you go from one, even if you have the best curriculum kits out there, from one kit to the next, there's not much connection. You're not clear as a kid why this is all science, because it seems different every time. You want to base your work on the results on learning. I've already talked about the all students, but it's not just what do they need to know, it's what do they need to be able to do. And finally, how does this learning build consecutively and coherently across multiple years of school. This was our challenge. How do we design science that has these properties? Well, what we said is science has 3 dimensions. How many of you have heard about 3 dimensions? Approximately half. Well, I'm going to spend some time talking about what each of the dimensions are and why they are. The 3 dimensions are the scientists and engineering practices, what scientists and engineers do, but also what students need to do to make this knowledge their own and really be able to use it. Secondly, the cross-cutting concepts. These are ideas that cut across all of science that we usually forget to teach. We think the kids will just get them. Like, science is about deciphering mechanism of cause and effect in systems. We don't tell anybody that. We just go from one system to the next and talk about what's going on here and what's going on there. And the idea that this is the basic thing that science is trying to do is never really explicitly discussed. We want to make it more explicit, more obvious, and use it, develop it as something kids can use as a tool when they come to the next problem. We'll see that later. And then, of course, there's the core ideas. We said, of course, students need to learn what scientists have developed and understood over multiple hundreds of years of hundreds of sciences working. But we want to pick the things that have the most strength to provide a foundation on which all future learning can build. We don't necessarily want to tell them everything, but we want to build a firm and solid foundation so they can learn whatever they want to learn later. That's the role of K-12 schooling. It's the goal no matter what subject you're in. So the idea that picking those things that have the most power to take you further and making those the focus of what you're doing in K-12 science means that sometimes things that you've taught and love to teach aren't there. But other things, and by the way, when you say that aren't there, you have to be very careful about that, because you can't read it all by just reading the standards. If you read a standard at high school that says the students will use the periodic table as a model too, well, you can't use the periodic table as a model to do anything unless you've got a whole lot of learning that led you to the point where you understood that model and could apply it. So even though it doesn't say you're going to learn this about acids and bases, or you're going to learn this about the properties of chlorine and hydrogen and how they're different, you're going to have to learn those things in order to be able to use the periodic table as a model to do anything. So don't try and read the standards as being, this is all you need to know. Think about each standard as, what do I need to know in order to be able to do what this standard asks me to do? And then you'll see there's actually more there than meets the eye in some subject areas, because the standards are sort of picked out as being choice important things that you have to build towards to get there. So don't try and make your curriculum today, I'm doing this standard today, I'm doing that. You have to really connect and build a coherent curriculum that builds to the standards as the outcomes. Now, why 3 dimensions? I love this quote. Henri Poincaré was writing, he's a famous French physicist, mathematician. He was writing a paper that was called On the Need for Theory. But really what he said is, theory isn't everything, right? He says, the knower must organize the knowledge. One builds science from facts as one builds a house from stones. But a collection of facts is no more a science than a pile of stones is a house. You have to build the house of knowledge. Of course you need the facts to do that, but you need more than the facts. Every student, in fact, has to build that house of knowledge. They have to build a coherent worldview of science in their brains. And to do that building, they need tools. And they need methods. And they must go from their initial preconceptions, which is based on how the world seems to behave, to a more scientific conception. The only way to do that is by going through this process of construction and deconstruction and construction, taking what you thought you knew and applying the scientific process to change it into something different. So they need the building materials, they need the core ideas, but they also need the methods and tools and practices to put them together. And finally, you can't build a house no matter how much equipment, how many planks and hammers and tools you have. You cannot build a house unless you have some idea of what a house is and where you're trying to go with these planks and tools. So the idea that you have to have some big picture concepts which apply in general and give you guidance and give you questions to ask about, okay, where in this house am I going to put the place where the cooking is done? Right? You have to be able to think that through to build your house. And the same in science. You have to have the questions you can ask and the metacognition to put things together. And that's what the cross-cutting concepts are designed to help you do. All of this leads to a different vision of how a science classroom works. We've talked before about inquiry-based learning, and many classrooms have some level of that. But the science and engineering practices define inquiry in a much more complex and complete way than most classrooms have reached in the past. We've talked about various things. This is very similar, if any of you are used to the 3 E's or 5 E's method of teaching science. Start with a phenomenon. Orchestrate the student work, this is the teacher's job, to make it happen so that the students from that phenomenon are asking questions, building models, engaging in scientific practice, with the purpose being to understand what happened in that phenomenon. And along the way, in order to do it, they're going to need to learn some science, because you've chosen the phenomenon very carefully so that in order to explain that phenomenon, they need the science you want them to learn. And so there's a place for where the teacher provides that science in the context of trying to explain the phenomenon, where it sticks a lot better than when it's just provided as this is something you need to know. Engaging the students in the practices, the teacher does a lot of questioning and not a whole lot of answering, because the students are the ones who are using the resources to develop and explain the phenomenon. Students do more talk and more activity. They do a lot of working in groups. They have to develop their own models. Why? Whenever we try to explain anything, we're working from some kind of mental model of how the world works. And until we make that mental model explicit as a written down model of some kind, and that can be a diagram, that can be some words, that can be all kinds of different ways you can express your model. But until it's explicit, it's not going to change.